at the University of Vienna and also scientific director at the Institute for Quantum Optics and Quantum Information of the Austrian Academy of Sciences, which is kind of the Austrian equivalent of IBS. So let me give you a little bit of background. He studied physics and philosophy at the LMU, one of the two universities in Munich, in Germany. He got his PhD in 2002. And then he joined the group of Anton Zeilinger with a Humboldt Fellowship. I have one then. Lukas, where is he? There he is. Right, this is the way that German can go outside of Germany to get a postdoc somewhere else. And I think then you basically worked your way up in that community of Vienna. And of course, many of you know Anton Zeilinger got the Nobel Prize 2 years ago, or 2 years ago for experiments with the entanglement of photons. Let me briefly tell you some of the accolades of Markus. So 2 or 3 ERC grants. As you know, the ERC grants are kind of the biggest thing for funding in Europe, including the Synergy grant in 2020, which is a collaborative grant. I think it's the biggest one of the ERC grants, right? And then in 2015, the consolidated ERC grant, and earlier the what's it called? Starter grant, right? So these are the 3 levels of ERC you can get. I also like 2017, the Science Prize of the City of Vienna. That must be a big deal. Sounds really good. His research topics are exploring the boundaries of quantum physics and gravity, especially with the focus on nanoscience also. So you know, we are kind of matched at this quantum and nano endeavor. But he really likes to focus also on gravity, so combining this quantum science with gravity, which is of course super exciting. And we met in 2 or 3 years ago, I think, in San Sebastian at one of his summer schools on I don't know what the topic was, quantum science or something like this. And so I invited him to come here, and he said, "Yeah, great." So this is actually the visit for this, and I'm really glad that you could come here.
Same here. Andreas, thank you so much. Thank you for having me. It's really a great pleasure. It already has been an absolutely fantastic day. Lots of labs, lots of discussions. I'm really enjoying my time here. So thanks a lot for all the hospitality. So now for something completely different. This has really little to do with what we have been discussing today. But nevertheless, let me start by taking you on a historic tour. Let's go back 120 years in time. So this was the time where quantum physics has just started its success story by describing atomic phenomena and by using Maxwell's theory of electrodynamics to describe light interacting with the newly found quantum structured atoms. Then came Einstein with his famous 1905 paper on a heuristic viewpoint concerning the creation and transformation of light. So the point that Einstein was making is he actually considered light, black body radiation in a black box, as a container where you ask now the question, what is the entropy of the radiation in that container? And he realized by very simple thermodynamic arguments that when you change the size of the container, then the entropy of the radiation changes. And that is something that you can classically compute because we had already the laws of black body radiation back then. And so you can compute how entropy of the radiation scales with the volume in the container that contains the radiation. And what he found out actually was that entropy changes with volume in the same way then an ideal gas changes. So you remember the formula for the ideal gas. Entropy change is just the ratio, the logarithm of the volume ratio of the change of volume divided by the times Boltzmann constant. And the same you have here for the black body radiation, and you see that the exponent in the volume for the ideal gas is just n times is the number of particles. And for the radiation, it just comes out of the blackbody law, is U, it's the energy divided by some constant. And the constant scaling with the frequency of the radiation. And so Einstein concludes in 1905 that monochromatic radiation behaves thermodynamically as if it consisted of independent energy quanta of magnitude a constant times frequency, which we now know is Planck's constant. Well, this was the content of his famous 1905 paper. And then in an appendix 7 of the paper, he applies this idea actually to the photoelectric effect and comes up with a prediction, the correct prediction for the law of the photoelectric effect. But in the end, it was simply a thermodynamic, beautiful thermodynamic argument. So to make a long story short, that did not go down very well. Everyone hated it. Yeah? So here's Max Planck. The rejection of Maxwell's electromagnetic waves seems to me to be a step which, in my opinion, is not yet necessary. So this is 4 years after Einstein's paper. Okay, 11 years after Einstein's paper, Millikan, Einstein's bold, not to say reckless light quantum hypothesis flies in the face of the thoroughly established facts of interference. 20 years later, okay, 20 years after Einstein's paper, Bohr, even if Einstein sends me a cable that an irrevocable proof of the physical existence of light quanta has now been found, the message cannot reach me because it has to be transmitted by electromagnetic waves. So people really did not like it. And this is the who is who of the community. This is now 20 years after the publication. And then, well, the story continues. Then, of course, we had phenomena that we that then were because so the quantum theory of electrodynamics evolved, and people acknowledged that there were effects like lamp shift, like the G2, like also then again the photoelectric effect that were sort of irrevocable proof that you had to use a quantum theory of light, and so things seem to have slowed down in the 1950s, then around 50 years after the paper. But that changed again in the 60s, when famous people like Chains came up with explanations, again, of all the phenomena of quantum phenomena of light using classical theory of radiation. This was Chains' famous neoclassical theory of radiation. And there was a very famous conference in the 70s now, and the Rochester Conference in Optics in 72, where Chains said, physics goes forward on the shoulders of doubters, not believers. And I doubt that quantum electrodynamics is necessary. So now we are talking 65 years after Einstein's paper. Still a big dispute in the physics.
Nobel Prizes given for quantum
there have already been Nobel Prizes for electrodynamics. Yeah, quantum electrodynamics, no doubt about that. Yes. And the actual question that was asked was the one you see in red. Can we have an experiment whose outcome cannot be described by the joint assumption of quantum theory and Maxwell's theory of the electromagnetic field? And Chains was of the opinion, no, here's a theory that actually can explain everything. Again, this was a so-called neoclassical theory. And Clauser, also at that conference, John Clauser also received the Nobel Prize 2 years ago, actually was the one standing up and saying, no, it is necessary. And Clauser was the one then who in the 70s presented a couple of experiments using twin photon sources, from atomic cascades, showing for the first time unambiguously that you need the light quantum hypothesis by demonstrating for the first time sub-Poissonian features of light in those famous experiments. And later on, there were also experiments by Alain Aspect in the same direction, plus also around the time the first Bell experiments emerged that also you cannot essentially explain by a classical theory of light. So that settles the question in the 1970s. Okay, so my point being, it took almost 70 years after Einstein's light quantum hypothesis paper to have an experiment that would unambiguously show that that a classical description of light cannot be used for a certain set of experiments. So, which brings me to the second part. Namely, we have also a situation today where we have a theory that works wonderfully, quantum theory. Here's a beautiful example from the Markus Arndt's group in Vienna, where you can see a consequence of quantum superposition at work on the level of a single large molecular system. So where the spatial superposition of a large molecule in such an interferometer results in interference fringes, and really shows that the quantum superposition principle can be applied on the level of individual molecules. So quantum theory works. At the same time, we also know that general relativity, as our current theory of gravity, works. And we know that both on astrophysical scales, where it is the basis for cosmology, for large-scale gravitational phenomena, for strong field phenomena, and even on Earth scales, where one of the most beautiful examples, as you all know, is of course the recent demonstration, this recent direct detection of gravitational waves that really shows the field character of gravity, where you have gravitational energy being radiated and then being detected again, and even with a time delay in the detection of the two sources, where you can really see that the gravitational wave propagates with the speed of light. So it is a field theoretic effect. So this is a situation we have today. Again, we have two theories that beautifully, both of which beautifully work in independent experiments, and they even work together. So we have experiments where we can wonderfully assume the joint validity of quantum theory and of general relativity as a classical theory of gravity. So, for example, this is one of my absolute favorites. There's this beautiful experiment where you probe the influence of Earth's gravitational field on a single quantum object, a neutron in that case. This is the famous cow experiment after the initials of the authors, Colella, Overhauser, and Werner. So what they do is they have a single neutron, and the neutron propagates through the gravitational field of the Earth. So this is a quantum mechanics 101 problem. You have a quantum particle, and it traverses through an external classical field. So what happens? It acquires a dynamical phase. So while it traverses. So the problem is, of course, we cannot measure a global phase. So what do? We can only measure relative phases. So we take the neutron, the wave packet, and split it in a beam splitter. And what we can measure is now when one branch of the neutron in our superposition traverses through one part of the gravitational field, the other one through another part of the gravitational field, they acquire different dynamical phases when they go at different heights. And then if you recombine them again after some time, you can actually measure the phase difference between the two different heights that the neutron has collected. And this is what they do in these experiments. So what they actually have here is a neutron that hits a slab of a single crystal silicon. So what you have here, this is a real photo. This idea of the neutron interferometer was actually invented by Bonse and Rauch in Vienna. This is a single crystal silicon here, and it simply, you cut here those two holes in it, such that you have three slabs of single crystal silicon. A neutron comes in. What happens is you have Bragg diffraction at the crystal lattice of the silicon. So you have a first diffractive order, and you have a transmitted beam. So you split the beam here in two, the transmitted one, the first diffraction order. Then the next silicon slab, the same happens. So this actually acts like a mirror here. And then here you recombine again. So you just build an interferometer for a single neutron. And since these two arms now, these two branches of the neutron, when you rotate this thing, so this is why it's like a half semicircle here. When you rotate that thing, you see that the lower branch traverses through a different height in the gravitational field than the upper one. So as a function of the rotation angle now, you acquire a different phase shift when you propagate through the gravitational field. And so what you see here as a function of rotation angle of the interferometer is a gravitationally induced interference fringes on the wave packet of the neutron. So wonderfully, GR and quantum physics are at work. Another beautiful example is gravitational time dilation, where you take a clock, an optical clock, which an optical clock is nothing else than an optical table full of stuff, and then you measure a frequency. And what happens now when you take this table here and you lift it up in Earth's gravitational field? So this is what they did. You see, they just typical checks with which you lift a car. They put it under the optical table and they just lifted the whole optical table by 30 centimeters. And here's the measurement. You see here, you measure frequency, and then whoop, you lift the table, and suddenly the frequency of the clock changes. And so basically, back then, they lifted the table by 30 centimeters and could actually see the relative change in frequency in the optical clock. This was around 2010 or so. This was in Dave Wineland's group. And if you look at the literature today, then you will see this is a recent paper by Juni's group in Boulder. They are now sensitive actually to the change of height in the lab by 1 millimeter. So they can resolve gravitational time dilation by 1 millimeter in the lab. That was a question.
Yeah. Do you need general relativity here to describe the experiment, or classical guiding will be the same?
So in that case, so the same, by the way, also for before. In both cases, Newton is sufficient. So both for the gravitational redshift and for simply the gravitational potential is in both cases Newtonian. Obviously, Newtonian is consistent with the full Schwarzschild metric, but since it's massive particles, you're totally still within the Newtonian regime. Yes. But of course, the point is, in a metric picture, already the time dilation is inconsistent with a flat metric. So it's basically already getting fuzzy. Yeah. But you're right, this is all Newtonian regime. But and this is my message. Okay. So right now, these are the most simple experiment. But so if you would now do the cow experiment with photons, you would need full GR, because for the photons, you get this factor of 2 in the light bending, because you not only have a change in the photon behavior due to the redshift, but also due to space-time curvature. So, and there are experiments right now who want to do that, who want to measure the cow effect with light, and there you need full GR with quantum electrodynamics. And so my point being that, but still with those, even with those experiments, then you can describe them by assuming the validity of quantum theory and the classical theory of gravity. And now coming back to my historic example, this of course now begs the question in the same spirit than before: can we have an experiment whose outcome cannot be described by jointly assuming the validity of quantum theory and GR? Okay? And this was a question that was famously asked again by another famous conference in Chapel Hill in 1957, even before the Rochester conference. So in 57, an Austrian physicist was there, Gold, gravity person, who exactly phrased that question. Can we have phenomena which a classical theory of gravity is unable to explain? And then Feynman was also there at the conference, and in his very inimitable style, of course, immediately said, yes, of course. Right? Went to the blackboard and sketched the following thing. He said, so what about if we have a mass? Like our neutron, okay, but just a little bit more heavy. We have a mass, and then somehow we have a device, like this is sketched here like a Stern-Gerlach device. So the mass is a spin, for example, and then you have a Stern-Gerlach, and you create a superposition, a spatial superposition of the mass being up and down, the two branches, like in our neutron diffrometer, just with a more heavy mass, okay? And so you prepare now this superposition. The mass here is down and up. And then you have a second mass, okay, that gravitationally couples to that mass. And now it's a very simple question again. So what happens? What do we expect? Well, what happens is gravity is at work. So what's going to happen is that we will have gravitational acceleration on the test mass depending on the state of our source mass. Right? So the down source mass will couple to the test mass, the up source mass will couple to the test mass, and eventually, after some time has passed, we will end up in an entangled state. Right? So the two each of the two branches will become correlated through gravitational interaction. Since the gravitational action is different for the two branches, you will end up in an entangled state. So after some time it's entangled, and the point is now, this entanglement can only arise if you assume that the gravitational field itself that mediates this coupling here, is also in a superposition. Because general relativity as a classical theory of gravity tells you that however my source mass configuration looks like, doesn't matter how, okay? You just put your source mass in a black box and you do whatever you want inside that black box. Then the gravitational field outside of the black box will be well defined in a classical sense, in the sense that there is a well-defined metric within which a test mass will follow a geodesic in free fall. This is an outcome of any classical field theory. But if I start out now with a system where my mass is in a black box, my source mass and my test mass, and those two are separable, and if my test mass will always only follow a geodesic motion in a well-defined metric, it will never become entangled. It cannot become entangled by definition. So that means that the metric that my black box here generates has to be in a superposition in order to generate entanglement. And the metric in a superposition cannot be explained by a classical field theory of gravity. So now this is our experiment. If we now were able to create entanglement through gravitational coupling between two quantum systems, then this would be an experiment that cannot be explained anymore by a classical field theory of gravity. This would be our example. So this was Feynman's example in 57. And there are many, many nice write-ups of those effects in the literature. Now, this is so much now for theory. Okay, so basically you see the theory is like 2 lines, and now we can refine it a little bit more. Now we need to write down essentially a possible experimental setup. Right? So Louis Witten was also at the conference, and he phrased it in a language that I think we resonate with, right? So what prevents this from becoming a practical experiment? This is what Witten asked Feynman. And so now in the literature, you find more and more proposals how you could do such an experiment. And I sketch here 2 possible scenarios. Right? So the one is you actually start out with the mass in an harmonic potential, just an harmonic oscillator. The other mass is also an harmonic oscillator, and they just couple gravitationally. So it's 2 harmonic oscillators coupled via 1/r interaction, 1/r potential. Okay? This is something that you can write down very quickly. So the interaction is a 1/r interaction. You do Taylor expansion of this whole thing, and then the first relevant coupling term between the two is actually a coupling XX. So in the position degree of freedom, and an XX coupling we know from quantum optics very well. This is actually an entangling interaction. This generates 2-mode squeezing, so a so-called Einstein-Podolsky-Rosen state in position momentum between the 2 masses. So this creates entanglement. Okay? Now, the other possibility to create entanglement is you already start, like Feynman suggested, with a mass in a superposition of its center of mass degree of freedom. So I take my mass, I create, like in the cow experiment, I create the mass in a superposition of being here and there. Okay? And then once I can do that, I can also do it twice. Right? It's like you start with 1 qubit, then you can also do a second qubit and so on. So if you show it for 1 qubit, you take a second one, and you place them next to each other and let them again gravitationally couple. And the point is now, this is again now our cow experiment. There's a cow phase. You see that this mass here will, just as a function of time, will actually acquire a dynamical phase that depends on the gravitational potential sourced by this mass. But this mass is in a superposition, right? So you see there you already get a conditional phase depending on what your state of this system is. The same is true for that, And if you write down everything, then basically what you get is your initially separable state of those 2 qubits actually becomes entangled. And if you write down the full dynamics, this is actually equivalent to a C sine gate. Right? So basically, a sign gate is nothing else than a conditional phase shift, and this is what you have here. Here, the conditional phase is actually the cow phase through the gravitational interaction, and once the phase evolution gives you a pi, then if your target and your control qubit start off in 0 plus 1, then the output of a C sign gate is an entangled state. This is exactly that, just in a different language. Okay, so and obviously we can compute now the rate at which that entanglement happens, because we have everything, right? We have the delocalization here, which gives us the strength of the coupling, or the difference in the strength of the coupling. We have the distance, and that's it. And we have the mass. And it turns out that for both cases, even though they look physically very different, the rates at which they entangle are exactly the same. So the entanglement rate scales with the ratio between Newton's constant and Planck's constant that somehow must enter. The mass square makes sense, no, because it's actually the two masses that couple with each other. The delocalization square, this is like two driven oscillators. It's the magnitude of the amplitude that enters into the coupling, and 1 over d cubed, because it's essentially the first relevant term of the Taylor expansion of a 1 over r. Right? This is where the 1 over d cubed comes from. And you generate entanglement when this rate here is larger than all the decoherence rates in your system. That's it. Huh? Makes sense. And now let me
talk about how you initialize the system?
Yes. Briefly. Yeah, I will. Good. But just to give you a feeling now, okay, about the numbers. Let's assume we have 2 atoms, okay, and we separate those 2 atoms by 1 micron. Okay? Atoms are delocalized by 100 nanometers, approximate wave packet size. Then the question is, how long will it take for the 2 atoms separated by a micrometer to become entangled via gravity? Okay, can you read it? 10 to the 24 seconds. Yeah, lifetime of the universe is 10 to the 18 seconds, approximately. Yeah, so bad. However, if we now go to 2 lead spheres that are approximately 50 micron in size, so this is approximately the Planck mass, 10 to the 18 atoms per mass. Okay, if you have two masses with each 10 to the 18 atoms, and separate them by 100 micrometer, okay, and delocalized by, let's say, 10 nanometers or so, then you see they become entangled in 10 milliseconds. Now you're talking. Okay, I mean, of course, you exchange one parameter of insanity with another. Right? And on the one hand, there won't be coherence times and experimental times on the order of 10 to the 24 seconds. But the question is, on the other hand, how realistic is it to think about 50 micron sized objects with a 10 nanometer delocalization? Okay, and this is it's the second question that I'm now trying to address in the rest of the talk. Okay, so in order to do that, I make 3 more experimentally motivated assumptions. Okay, and before I do that, I rewrite our entanglement rate just for convenience in the following way. I don't talk about decoherence rates, but I talk about coherence times. Okay, but this is a language that is more, I think, natural to all of us. And so I'm just rewriting what I just had in this condition. So I basically put the constants on one side and the experimental parameters on the other side. So what I get now is, this is the necessary precondition in order to generate entanglement via gravity. The mass square, and I assume now that the 2 masses are of the same size. Delocalization square, I assume now that the amount of delocalization is the same in both cases, times coherence time, times 1 over d to the 3, d is the distance, needs to be larger than h bar over g. So Planck's constants over Newton's constant. Okay, so and the beauty of this expression is we can separate that in 2 different experimental endeavors. You see on the left hand, a mass delocalization times square root of decoherence, square root of coherence. This is a number that we want to maximize, and we want to, and this we can maximize in quantum experiments. And we don't even need two particles interacting. We just want this number to be large, right, for a single particle. So the quest is, let's do quantum experiments where we just make the mass as large as possible, the delocalization as large as possible, and the coherence time as large as possible. Okay, let's just maximize that. This is in quantum experiments. Then the second thing, I need to make this thing large also. So and what is this? Well, this is actually the distance in gravity experiments. So I need to be able to do a gravity experiment where I can isolate gravity as a coupling interaction. So I need to be sure that the coupling that I see is dominated by gravity and not by electromagnetic interactions. And this I need to do at a distance d, and I need to make d as small as possible. Okay? So, and there I don't need to do any quantum. I just need to build gravity experiments where I learn how to make d as small as possible. And what we are doing right now in the lab is actually we are doing exactly that. We have quantum experiments that try to maximize the left one, and we have gravity experiments that try to minimize d. Okay, so now 3 additional experimental considerations. Consideration number 1 brings me, yeah, go ahead.
This conference in 1957, they actually went that far to figure this all out. Already.
Say again, the 57?
The conference.
No, this was just, this was all prose. So basically they discussed that, and actually there's a transcript of the whole conference that has been republished just 10 years ago or so by the Max Planck for the History of Sciences in Berlin. And there's a full transcript of the conference. This was organized by Bryce and Cécile de Witt. And Cécile de Witt actually kept all the tapes of the conference, and Dean Rickles and Cécile de Witt actually transcribed the whole thing. But everything is there. So the numbers is something that basically now I think this topic sort of re-emerged 10, 15 years ago, together when the transcript of the Chapel Hill proceedings were republished. And then, so this is a back on the envelope calculation, right? So, yeah. I mean, the point is, once you take it serious, you can write that down immediately. But back then at Chapel Hill, Feynman actually says that another point about all of that is there will never be experiments in that direction. What Feynman says literally. Yeah? And since there won't be any experiments, we now need to push theory to the extreme and see if we can learn something there. Yeah. By the way, the second topic at the Chapel Hill conference had 2 main topics, main questions. Number 1, do we need a quantum theory of gravity? And the second topic was, do gravitational waves exist? And actually, Weber, the guy of the Weber bars, he was actually inspired by the conference, by the Chapel Hill conference, to come up with the idea of resonant bar detection with the Weber bars. And then the rest is history again. Okay, so here come my 3 experimental additional considerations. The one is already very clear there for most of you here in the room. The one is obviously a noise challenge. Okay, so we know displacement noise exists, and we know that we want to avoid it. Okay, so I give you the reason why. In your case, it's clear. No, so for all the scanning probes, you have a tip and a surface, and you want to minimize the fluctuations. In our case, consider the following: you have an atom in its ground state. Now, this is something people can do all around the world. So typically what you have is you have an optical trap in which your atom sits. The typical trap frequency is a megahertz. Then you have the atomic mass, which gives you automatically the ground state frequency, ground state energy, and the ground state size. And the ground state size of a typical atom in a megahertz trap in an optical lattice is normally in the order of 100 nanometer. Okay? So if your lab now shakes by a nanometer, you don't care. It just doesn't matter. Your wave packet is like that big, and if you shake a little bit, who cares? Okay? So stabilize everything down to a nanometer displacement level, the world is fine for you. So now, instead of taking a single atom, you now take a particle with 10 to the 12 atoms. Okay? So this is what we want to do. So suddenly, the ground state size scales with 1 over the square root of mass. So suddenly you have a 6 orders of magnitude smaller ground state size. So instead of having 100 nanometer, suddenly you have a picometer ground state size. Okay. Now if you have now a picometer wave packet size in your ground state, and you shake by a nanometer, all hell breaks loose. So you cannot have that. So this is why displacement noise for experiments with the center of mass degree of freedom, it's just a single degree of freedom. It's a massive object where you want to have pure state wave packets, where you have that amount of that small wave packet size, you need to be extremely low noise. So this is why experimental boundary condition number 1 avoids displacement noise. And what does it mean? Well, these curves, you all know that, right? So basically it means do not work at low frequencies. It's a killer. Okay, I will show you later our gravity experiments at 10 millihertz. God, this is the most painful thing you can ever do. So boundary condition number 1, avoid displacement noise. We want to work at frequencies beyond 10 hertz. Okay, anything else we just ignore totally. We don't want to go low, but that also means the duration of our experiment needs to be short. So it means we want to operate at timescales on the order of 100 to 10 milliseconds. Okay, boundary condition number 1, which translates into we only want to be sensitive to frequencies above 10 or 100 hertz. Okay, so this bounds the coherence time already. Okay, which is not so bad. So number 2. Electromagnetic shielding. We are going to do gravity experiments. Okay, and since we do gravity experiments, we need to exclude electromagnetic interactions. How do you do that in gravity experiments? You put, you see here are our 2 masses, right? And so how do you avoid electromagnetic interaction? You put a Faraday shield between, right? Which is just a conducting, it's just a conductor. The better it is conducting, the better. So what happens is any sort of charge distribution on that side, when you creates a mirror charge on the Faraday shield, which creates some DC electromagnetic field. However, when you move your charge distribution through moving the mass, you change the mirror charges, but you don't change the overall field distribution. Right? So basically, there's only going to be a DC bias, but there's no position-dependent electromagnetic interaction on the other particle. So where are we today? Today, the smallest distance at which gravity has been measured in the lab is 50 micrometers, 50. This is huge. Okay, and this is in the pioneering experiments by the group of Eric Adelberger, the famous Earth Wash group at the University of Washington, and they typically have some gold-coated membranes, beryllium copper in that case, so 10 micron thick, and then gold-coated, and then basically they try to come close, and they have patch potentials, and everything goes haywire when they come closer, and so on. So this was the limit they could achieve. So we are now planning an experiment where we want to decrease this distance down to 10 micron. So this is at the moment, this is our goal. And we have a standing bet with Eric. Eric says there's no way we'll be able to go below 10 micron. And so this is what we want to do. I want to go below 10 micron. But I still put conservatively 10 micron is like our limit. And this is now our second boundary condition. The second boundary condition is we need a Faraday shield, which means that we will have a lower bound on the D here, right? Because D can at most be as large as the distance to twice the distance to the Faraday shield. And so the gravity, this one here will also be bounded. This is boundary condition number 2. But there comes something with that because there's a bound. And now comes number 3. Now let's combine coherence with a charged surface. Right? I know you are operating at different distances, but I think we share sort of here similar problems. Our problem is, imagine now we have our charge distributions, our delocalized mass, okay? And our delocalized mass sits now at a certain distance over our conducting Faraday shield, which we already said we need to have. So what happens is the charge distribution here will create mirror charges. And whenever there is the slightest amount of dissipation, means that there will be which way information, so to speak, leak into the environment. So any sort of dissipation in this conducting shield will lead to decoherence of my delocalized state. So this brings me to my final experimental boundary condition. I assume now that the decoherence will scale with some order of delta x over d. And d, so d is the distance, delta x is delocalization. So it means I need to keep my delta x over d, so that the amount of delocalization versus the distance, I need to keep that small. Okay, that allows me to sort of minimize decoherence. And that still needs to be numerically checked, but this is, I think, this is a relatively clear boundary.
You mentioned that you form the mirror charges in the Faraday shield. So
yes.
how do you prevent a joint interaction between the particle and the Faraday shield?
How do I
prevent?
I don't. No, I don't. So yeah. So there's always going to be some DC interaction between the Faraday shield and the masses. But this interaction will be DC. So this will at most generate in a quantum picture, again, a global phase. And it is totally position independent. So since it's position independent, it cannot generate entanglement in position momentum degrees of freedom. So there is an interaction, but it will be decoupled from the entanglement generation. Yeah. So now I showed you with three very simple and I think conservative and meaningful additional boundary conditions. We have now bounded the coherence time, we have bounded the distance, and we have bounded the delocalization. So which gives us now, all putting together, a condition on the mass. If I want to fulfill all my three experimental constraints, I put the three things together, then I arrive at the following simple formula. My mass needs to be larger than the Planck mass times this expression, which is on the order of 10 to the minus 6 times the Planck mass. What is the Planck mass? The Planck mass is 10 to the 18 atoms. That's around 25 micrograms. And that means I need to have at least 10 to the 12 atoms as a mass in order to make that experiment working. Which now I summarize everything I said right now. So in order to have quantum systems as sources of gravity that allow me to make a meaningful experiment, in meaningful meaning, I want to do an experiment that cannot be explained by assuming the validity of both quantum theory and the validity of GR in its present form as a classical field theory. I need to answer the following questions. Number one, how small can we make a source mass in gravity experiments and how close can we bring them together? And number two, how massive can we make a quantum system and how strongly can we delocalize it? Okay, so this is essentially, and these two questions are being followed in my group with a set of experiments, basically trying to answer both of these questions. Okay, I will briefly say something to gravity. Right? So gravity experiments normally involve large masses. So if you want to do a gravity experiment, so here's an historic example, one of the very first experiments. This is actually a redo of an experiment that was done even 50 years before that in South America. This was an experiment by someone called Maskelyne in Scotland, where they measured the gravitational attraction between a pendulum, mass on a pendulum, and a mountain. They really ran around the mountain and measured the displacement, the deflection of the pendulum towards the mountain, which, by the way, is very funny. In Scotland, they call it a mountain. I think it's like 800 meters below ground or so. Yeah. For someone coming from Bavaria, I always have to laugh at this. And that, of course, evolved into the famous Cavendish experiments and so on, and modern day experiments that measure, like, with incredible precision, Newton's constant, for example, typically have these large masses with kilogram scale, well-defined sources of gravity. So our question was, how small can we make things? And we started with a very simple idea. So what about when we start with a gold mass, okay, like that, of that size, and then we just take a second mass, and then let's just shake one, and then the other one experiences a gravitational acceleration, and then we just measure this shaking up of the second mass. And we just need to make sure that we isolate those two well enough. But basically, having that one here, you know, again, separated by a Faraday shield, and here having some sort of oscillator that is free. Eventually, we first wanted to have that as geometry, but then at the end of the day, it became a small-scale version of a Cavendish experiment where you have this torsion balance with these two gold masses on a small silica rod. And you see here the other gold mass here separated through a Faraday shield. This was also just a gold-coated aluminum foil in that case. You have a displacement modulation here of the mass by a few millimeter. The smallest separation between the two mass surfaces is around 0.5 millimeter. And if you put in the numbers, then you have an acceleration modulation here on the test mass of on the order 10 to the minus 10 meter per second square, so 10 to the minus 11 G. And if you, in terms of displacement, that's a few nanometer displacement of this pendulum. And the pendulum had a resonance frequency of like 10 millihertz. Okay, so you can imagine if you want to wait and see how this thing displaces by a nanometer at 10 millihertz, and you do that just in a regular lab, then this becomes a very funny undertaking. So you see here, this is a picture of our pendulum, and here is real-time data of our pendulum. You see this just displacement noise, and you see that the variance becomes smaller here, right? It becomes smaller because this is night. And then the typical things, right? You see here, this bump, that's a night bus, that's a night bus, that's a late night bus, you see? So basically, and our lab is like 70 meters away from a road crossing. Yeah, during the day, it was just impossible. So I think the press called us the most expensive traffic monitoring system of Vienna. Then we also had, of course, a city tram. I now know what a city tram weighs, 90 tons, a Vienna city tram. If a 90-ton city tram passes your lab in a distance of 100 meters, the gravitational pull that it exerts on your test mass is of the same order of magnitude than the gravitational pull of a millimeter gold sphere sitting a millimeter away from a pendulum. So actually, it's the same noise. So signal to noise is becoming very close to 1 here. Right? Anyway, so say again. Oh, this is really just an optical lever here. Okay, this is just a very simple. This is the most simple setup you can think of. Just deflection with a lever. Yeah. So we measured then over Christmas, and what you can see here, the relevant one is the red. So the red is actually the force modulation. So you see we modulated off resonance here. You even see a second order, because what you do is you actually modulate a 1/r potential. So you get higher harmonics because it's a nonlinear potential, the gravitational potential that you see. So we could resolve it actually very nicely. At the end of the day, we could resolve 10 to the minus 11 G with a precision of 1%. So for first trial, that was nice. And what we are trying now is basically trying to get smaller. So this is our current mass size. So what we want to reduce it now is we want to go down to the Planck mass. So we now want to use this one as a source mass and actually measure the acceleration on a test mass of that size due to a source mass of that size. Now this is the next experiment. Obviously, we cannot do that in the Vienna city tram, in the Vienna city because of all the trams and buses. One possibility would be to move to one of Andreas's basement labs. Right? What we do in Austria, what we can do very well, we can dig tunnels. So we actually go in a tunnel. This is an underground facility. You see here, this is a concrete platform. This is Hans. Hans is actually just mounting the experiment. You see the cap that Hans is wearing because it's very cold. It's like a constant 7 degrees. Okay, but constant. Really, the temperature fluctuation is on the order of 5 to 10 millikelvin. This is amazing. But it's 4 experiments. It's stuck 4 experiments actually. Yeah. So there are 2 systems. One for magnetic measurements and the other one for seismic measurements. 2 tunnel systems. But the 7 degrees is also in summer. right? And if you forget that when you go there, it's a very chilly experience. So the noise performance is extremely good. So you can see here seismic noise is orders of magnitude down. But you can see here, this is a single traces. You see this one, this was an earthquake in Turkey, actually, what you see here. And the magnetic noise is, of course, down and so on and so on. So all of that is, and you see here, when you have something like an earthquake, then you see your pendulum suddenly is rung up. And then, you need to have means to bring it down again, because you have a 16 millihertz pendulum with now a Q factor of 10 to the 4. So if there would be now no active damping, then the whole thing would just ring down, forever. So here's our new mass. We have it now. This is a small microfabricated silicon cylinder of the size of a Planck mass that sits now on this disk, and this disk is now rotating in front of our torsional pendulum, and we are measuring as we speak and hope to see a gravitational signal of a Planck mass soon. So this is now basically this is the type of experiments we are doing. So in a scale of, we have here, let's say, masses in experiments. You see, for gravity experiments, this domain, previously the masses were more in the gram regime. This is where we are pushing it right now. And we think hopefully very soon this summer we will have pushed it down to the Planck mass regime. Right? So this is the current level of sensitivity. And then the next thing that we need to tackle is then also the distance. So right now, basically, for the these are similarly difficult topics, because what you want to achieve is isolation of gravity from all the other interactions. Okay. The second part is now the quantum part. What I have here, please apologize, excuse me for this just very rough sketch. You see, when you go to even smaller masses, then coherence time pops in, because they're quantum experiments where you have delocalization and the spatial degree of freedom of matter. This is the domain that I showed to you already, the matter waves of Markus Aspelmeyer with the macromolecules, large displacements, long coherence times for very small mass. Then you have, this is Andrew Cleland's talk in a month from now. He's going to be here, talk about that. This is solid states, mechanical systems, and but you see where this goes. There's a tendency that the larger you make the system, the more massive you make it, the more problematic it becomes. And this is what we want to fight. So let me put some numbers to what I just said. So here's the macromolecule experiment I already showed you. So basically a macromolecule with around 2000 atoms is being put in a superposition of like 500 nanometers. So it's really like being particle being like here and I don't know, over there next university. On the other hand, you have these, let me just show you the numbers here before I go down. If I now would hypothetically assume that I could take two of those delocalized molecules and bring them close together, 10 micrometer, and let them gravitationally couple, like our atoms before that we put together, and then ask what is mass times delta x squared times coherence time in units of h bar over g, and assuming that I have d equals 10 micron. That's the numbers I want to do. Then this should be on the order of 1 in order to make a meaningful gravity experiment or generate entanglement. And you see it's 10 to the minus 18. Yeah, because molecules are very small. Okay, that's the problem. So then you go to Andrew Cleland's lab, and he will show you in a month these beautiful systems and many more things. So this is a pioneering experiment he did back in 2010, where they had aluminum nitride slab. So this is now, you see, this is a bit visible to the bare eye. This is like a 50 micron cantilever. And what they did was they had this aluminum nitride sandwiched between aluminum, And the sandwich was such that the aluminum nitride can capacitively couple the superconducting qubit. So you have a two-level system now coupled to this slab of aluminum nitride, which is just an harmonic oscillator, thickness oscillations. And now you can cool it to the ground state. You can couple to the qubit, and you can generate energy eigenstates of this aluminum nitride slab. And you can even do superposition. So they nicely showed Ramsey interference. So they can generate 0 + 1. So superpositions of energy eigenstates of the thickness oscillations. But that actually involves different locations of the atoms in the aluminum nitride lattice. So basically what you have here is also a superposition of all the atoms being distributed like that, and then being distributed like that, where they are displaced from their actual configuration. So there's a spatial displacement involved. So what you have is now, you have a large object with 10 to the 13 atoms. Okay, so it's 10 orders of magnitude increase by going to solid state systems compared to here. However, with delocalizations on the order of sub-femtometer. This is the problem. Okay, this is why also in that case, the magic number is only in the order of 10 to the minus 24. And there has been a recent beautiful experiment by Yi Wen Chu's lab at ETH, basically a remake of that experiment, just larger and better. And she gets to the order of 10 to the minus 17. So this is what we need to bridge. So I don't want to bore you to death. So let me just give you the gist of the idea now that we are following. So number one, what I showed you now is that you see, like things like Andrew Cleland does with solid state systems are great because you have many, many atoms. Things like that Markus Arndt does are super because you have long coherence times and large delocalizations. Okay, why not combine those two? What is so great here? Well, it's freely flying, freely propagating atoms or molecules. Okay, what is the problem here? Here, this is a clamped solid state system coupled to the environment and harmonically bound by a very strong connection. Right? So here. So what about combining the best of the two possible worlds? Take a solid system, right? Here, take a solid system and levitate it. Have an external potential in which your solid state system actually rests. So you can have harmonic confinement for state preparation. And you can switch off the potential and have free evolution and have beautifully large coherence steps. And also large delocalizations. That's the idea. So this is why we started to actually levitate solid state particles. That's an old story. Eshkin already invented that in the 1960s. But now we are doing it in vacuum. So essentially we use optical tweezers. So what you do is you just focus laser light. There's a dielectric particle. So the point is dielectric means you induce a dipole moment. If you have an external electric field, the potential landscape that the particle sees is just d dot E. Right? So the dipole moment times the electric field. Since it's a dielectric, the dipole moment is induced. So it's the polarizability times the electric field, which means that the overall potential landscape is just E squared, so the intensity. And if the intensity is now a Gaussian beam, then the harmonic potential, you see that my particle sees, is just the inverted Gaussian. And so for very small displacements, this is just an harmonic potential. So this is why in a focused laser beam, for small displacements, the focused light acts as a 3D harmonic confinement for a dielectric particle. So it just trapped the particle and it's there, which is great because now you can do physics with it. We have now a confined harmonic oscillator. And I just show you something very funny. We've tried to figure out a way, how can we load those particles into our vacuum chamber without contaminating our chamber, because there were some very dirty things going on. So what we thought was, well, why don't we take a photonic crystal hollow core fiber? So we have now here a loading chamber, very dirty, where we load particles with a nebulizer. You have many particles. And then we have an optical standing wave in this hollow core fiber. And then we just let the particle propagate through a conveyor belt, an optical conveyor belt. And we just shuttle it into our science chamber where we then trap the particle. And you can see here, you see, there, boom, goes the particle. So basically we have a single particle. We can load it here. And then we just shuttle it. Can you see it? Boom, into the science chamber, which is particle by particle.
In the inside of an optical fiber.
This is the photonic crystal hollow core fiber. So basically, the idea is, because in a normal optical fiber, the point is you need to have a refraction high a high refraction index, small refraction index in order to get total reflection. And if the fiber is hollow, you cannot do that. Because, and so the solution is that you have a photonic crystal structure on the outside, such that you actually get total reflection at the interface. So and this is so-called photonic crystal hollow core fiber. It's hollow, and the nice thing is it can actually sustain pressure differences of almost 10 orders of magnitude. Yeah, so what you can have is, so here we have actually a chamber at a millibar. Here we have a chamber at 10 to the minus 10. And this is a leak that we have. This is open. It's an open leak. Yeah, but that's okay. Yeah, it can sustain that. You actually have a small flange here, and then it's a swedge lock. Yeah, with a plastic inside, and you just shut it, and you can sustain it. Yeah, very good. No, we don't need that. So what we do now? So basically, now we have the particle here harmonically trapped. Oops, where is it here? We have the particle harmonically trapped. And now what we do is we just read out the light, because there's a lot of light. There's light in forward scattering, there's light back scattered. And the point is that the light that is scattered back carries information about the particle movement, right? Because we just modulate the phase of the light. And what we do now is we actually have in our back plane, we built a detection system that is actually resembles a confocal backplane imaging that you know from microscopy. And we can achieve there, because of our high detection efficiency, essentially quantum limited position detection. It's only limited by the Heisenberg principle. And so since it's Heisenberg limited, we can now do a state reconstruction of the state by using a so-called Kalman filter. So basically it's an optimal state estimator used on a stochastic Schrödinger equation model that we have in the back. So we do a real-time data analysis on an FPGA directly on board a computer that provides us with an optimal state estimation while we measure the particle. And since the measurement is Heisenberg limited, it's basically in a Heisenberg microscope, we can resolve the position in phase space. You can see that here. We can resolve the motion in phase space with a precision given only by the ground state size. So it means we can now follow the quantum trajectory of the particle at room temperature. And you can also use that, of course, to feed back on the particle. And we do that, and basically we feed back such that we stabilize the particle in its quantum ground state of motion. So this is our state preparation. We can, by just using a Heisenberg microscope and active real-time feedback, prepare the particle in its quantum ground state of motion. So basically we prepare a pure state wave packet in a room temperature environment of 150 nanometer glass sphere. So that's around 10 to the 9 atoms. Okay.
So you effectively cool this thing down.
We cool the center of mass degree of freedom. So the sphere itself is still hot. The sphere itself has still like 500, 600 Kelvin because it sits in the focus of a laser beam, right, and is radiating like hell. But the center of mass degree of freedom of the thing, which is the thing that quantum mechanically is the one that we address, this is the one cooled to its quantum ground state of motion. So I need, in order to describe the center of mass motion, I need quantum physics in order to describe that.
And in all three directions?
No, this is just in the direction along the tweezer axis. Yeah. The other two directions we actually cool a little bit, but not into the ground state. So we treat this as a one-dimensional problem. Okay. And of course, so what could you do now? So the point is, what we need to do now is we need a largely delocalized wave packet. So one thing you could do is, you see, you could actually, this is our particle in the trap now. So we use the fact that we have an harmonic trap by laser light, we use to cool to the ground state. And now what you could do is you can just switch off the trap. This you cannot do with a solid state harmonic oscillator, right? So you switch off the trap, then you will have free fall, and then you see already after some 10 milliseconds, the wave packet size would already be larger than the particle radius in that case. So this would be one possibility to create now large wave packet sizes. Okay. Or you could also, these are proposals by Oriol Romero Izard, you could also switch on actually an inverted potential. Then you would speed up exponentially the growth of the wave packet. These are all possibilities. And how would you do that? Well, one possibility to do that is, this is the nice thing now about having optics. You see, I told you before that it is actually, it's the intensity of the laser beam that the particle sees that defines the potential landscape. So instead of having now a Gaussian beam, you have now another beam profile. Okay, let's see, you have this TM01 here, for example. Yeah, and this which you can easily do. You see how the intensity profile looks like, and the inverted intensity profile is just an inverted potential. Right? So you can just invert the potential just by changing the shape, the spatial shape of the beam. Or you could do, you can make a flat top beam, which is like a quartic potential. Or you can make a double well potential by just adding those two together. And so these are things one can play around with now. And the big questions that now we need to address is also, so how can we now prepare? So once we are there, can we go there? Right? So these are questions we're trying to address right now. You already mentioned our ESC grant. So this was the reason why we now have this collaborative grant between 4 different groups, 2 at ETH, Lucas and Romain and Oriol. Innsbruck, he just moved to ICFO in Barcelona. And so there are many things that we are working on right now, trying to actually come up with solutions how to do that. Very quickly, this is just that I have shown it. There are many proposals. We have written some of them 10 years ago at least. And there's right now also Ron Follman is actually, he comes from atomic physics, but he's trying to implement now really Einstein's, Feynman's idea of having a spin system and using a magnetic field gradient, so really Stern-Gerlach to do separation. So this is a very courageous endeavor. What we are doing, and then I'm essentially done. At the moment, I don't want to show you the details. I just want to point out one thing. We have now been working on a protocol where we, as I showed you here, so just look at the potential. We start with an harmonic potential. We cool to the quantum ground state. Okay. And now what we do is we switch off the potential, and then you have free evolution. We delocalize the whole thing. Okay. And then comes something that is very well known in optics, just classical optics. What we do now is we interact with a very short light pulse with our dielectric particle with a cubic intensity profile. And the point is that the intensity profile of the beam the particle interacts with is imprinted on the phase of the wave packet. So if you have, for example, just a Gaussian, a quadratic intensity profile, you get a quadratic evolution of your phase along the wave packet, and that is nothing else than a Fresnel lens. If you think about it, the spacing of the phase differences in a Fresnel lens is actually quadratic in distance, so it's actually a focusing effect. And when you have a cubic potential, it's a x to the 3. You get a phase variation imprinted with an x to the 3, and that is actually nothing else than a diffraction grating. So what we provide, a short pulse makes a phase grating on the particle wave packet, and this allows us to create interference fringes. So this would be a way to create spatial superpositions. We're working on that right now, and we think that all of that should work at 300 Kelvin and within milliseconds, right? So this is our point, that we need to have short timescales to do that. And nice thing, our magic number, you see, if that experiment works, then our magic number, mass, delocalization, Green's time, is only 10 to the minus 10. We need 1, okay? But look, the mass is still, this is a particle 50 nanometers, so this is 10 to the 8 atoms in that case now, okay, in there. So if we would be able to do this with 10 to the 13 atoms, mass enter square, we already have 10 orders of magnitude covered, okay? So this is why we are also looking into superconducting levitation. So what we have is in our lab, we have a lead tin sphere that we keep between 2 anti-Helmholtz coils. The whole thing sits in a Dill fridge. And you see we are levitating here. This is this thing here levitated in an anti-Helmholtz coil configuration at 20 millikelvin. Okay? And this is an object. This actually has 10 to the 18 atoms. Okay, and in principle, now we have an harmonically confined particle. What we do is we read it out. You see up there as a squid. So basically, because of due to the motion here, you get a modulation of the magnetic flux through the squid, which you can monitor. This is our detection. If we would be able to also achieve Heisenberg limited detection in that scheme, then we can play the same tricks with the optics and can do ground state preparation of a particle of that size. And then we are way above 1. Okay. So I'm just fantasizing here, okay? But I'm just saying that in principle, these 10 orders of magnitudes are not so completely implausible. So that's it, I'm done. Our challenge is then, of course, the decoherence challenge. I just want to show you this one here. You see, where I would like to go eventually is I would like to have a mass of 10 to the minus 3 times the Planck mass. This is like a 5 to 10 micron particle, okay? I would like to see it delocalized by 100 nanometers at environment temperatures of like 10 Kelvin. Environment temperature is important because of blackbody radiation and background gas. And these are the numbers, these are assumed solid state densities, 10 micron distance, and 10 millisecond operation time. So I think that's it. And just because I think Valeria was asking, I just put it up here. My brief summary. What I told you about now was one of 2 possible lab-based approaches to probe like quantum aspects of gravity. The one is the first one would be assume that there exists a quantum theory of gravity and then probe its low energy consequences. I have not talked about that. We have discussed a little bit today, but this is actually also a field that is growing. But the second one, and I prefer that very much, is actually don't assume anything about the interplay between quantum physics and gravity and directly probe the phenomenology when you try to combine those 2 domains. So that's it. And we do that by addressing those 2 questions. I already showed that to you. These are our 2 approaches. You see, we still have to bridge some orders of magnitude, but as I told you, orders of magnitudes are not a problem. And essentially a big thanks goes to my whole team. This is actually in Kaput, where the city of Berlin actually built a house for Einstein a long time ago. And this was a group trip there. So thank you very much for your patience and attention.
Thank you very much. Thank you. I think we learned a lot. Go ahead.
I have 2 questions. One is technical, another is between. Can you go back to the slide with the cubic potential? In the second square, after the free evolution, that one is a squeeze state, right?
Exactly.
What is the use? Like, why do you need the squeeze state in this experiment?
Yeah. So there are 2 aspects that are important. So for this experiment, the squeezing is important because I told you before the size scale here, right? So because it's a massive object, the size of the wave packet is picometer. And now what you have is you have an optical potential landscape, right? Where you exploit the nonlinearity of the potential landscape. But since this is optics, the length scale of the nonlinearities is on the order of 100 nanometers, and even more. So in order for the wave packets to actually explore the nonlinearities of the potential, the wave packet has to be on the order of the length scale of the nonlinearities. So otherwise, for a 3 picometer wave packet, any potential locally just looks like an harmonic potential. So that the nonlinearity would not show up. So you need a large scale wave packet in order to explore the nonlinearity of your potential. That's the reason.
Thank you. And the second question is, if we have a single particle and we put it in a superposition of space, let's say, if the gravitational field is quantum, then there should be some self-interaction, right? And this should give some, I don't know, some. Is it true?
If you have an electron or a charged particle in a superposition, bless you, will you have self-interaction between the two branches?
I would say so, and that's give some correction terms in some physical part.
Exactly. If this were the case, then you would have decoherence.
Okay, but you should be able to see some correction term.
Exactly.
In some
You should, but you don't. So I think so. The short answer is, according to standard quantum theory, there is no interaction term, right? Because what we are talking about is what we write down is different field configurations that are connected via probability amplitude. So these are not two real physical fields, but these are just each of the two field configurations is a solution of a classical theory like Maxwell or GR, but they are superposed in a quantum way, meaning there's a probability amplitude for this field configuration, a probability amplitude for that field configuration. And this is a linear superposition without any interaction between the two terms. So that's the point. Now we're talking about probability space versus physical space. But so this is standard quantum theory does not predict any sort of self-interaction. People predict the occurrence of self-interaction. So you find in the literature a couple of people saying, we don't believe that the gravitational field can be put in a superposition. And one possible solution or consequence would then be that you need to modify quantum theory. And one consequence of such a modification could be a self-interaction term. So Penrose actually favors something like that.
Thank you.
Yeah.
Other questions? We pass the mic.
Well, in a gravitational wave, if the mass goes to approximately the speed of light, we have to consider post-Newtonian correction. So in this paper, do we have to consider a post-Newtonian correction?
Now, unfortunately, no. And the reason is that all of these experiments, because of the short distance and the small masses, really operate in the low energy, non-relativistic Newtonian limit of GR. So any sort of retardation effects are simply too small to be seen. Because it's the quadrupole of the radiation that would be responsible for the retardations. Unfortunately, it's way too small. So this whole thing, the whole argument rests on the assumption that gravity can be described by a classical field theory.
And also, in a gravitational wave, we only consider a quadrupole moment. But I wonder that these consider only a quadrupole moment or
yes. Well, at the end of the day, again, so this is the again non-relativistic Newtonian regime, low energy regime, where you cannot distinguish the Coulomb terms or the static term from the propagating, the graviton-like term. So basically, because the wavelength is actually sort of longer than the distance, right? So this is why you do not, the creation of gravitational waves doesn't play a role.
All right, thank you.
But of course, I mean, in a quantum field theoretic description, right, the thing that is relevant is only always the quadrupole term.
Thank you.
Can I ask you again about your experiment where you sent this one particle into the other?
Yeah,
chamber?
definitely.
I actually asked myself, why is the particle traveling through this whole fiber?
Because you so it's a standing wave, but you detune the frequency of one of the arms. So it's called an optical conveyor belt. So basically, what you have is here, you have light coming from the left and light coming from the right, and that forms a standing wave. Okay, so if the two frequencies, if left and right frequency is the same, then you just have a standing wave. And if you now detune the frequency, where is it? Can you see it? If you now detune the frequency of that beam with respect to that beam, then the maxima will just shift. Okay, and then basically depending on the detuning, and since the particle is trapped in one of the maxima of the standing wave, it just taken along.
I see. And so why do we see it like on this video? Why do we see it like radiating? Is that really like black body radiation?
No. That's you see the light is actually 1064 in that case. So it's infrared, and that's just an infrared viewer. You look through. This is really the light scattered because it's trapped. This particle, so it's moving while it's trapped in the standing wave of a 1 watt laser beam.
Surfing.
Exactly, it's surfing the maximum. So it sits in a maximum of the intensity and just scattering light. Yeah.
Good. Other questions? I have one. So obviously these are extremely challenging experiments. How many people in the world can do these kind of experiments to really, try to do these quantum optics with macroscopic objects? I mean, of course, doing it with atoms, like atom trap and so on, that's a fairly sizable community, but what about going to this big things?
Well, I mean, there's a growing number of groups doing, let's say, macroscopic quantum physics in all different regimes. Right. So, for example, I mentioned briefly the works of Yves and Zhu now at ETH, doing this huge bars. Right. So not only like Andrew Cleland's aluminum nitride 60 micron, but they really go even larger. And so this is really a large object, but the displacement is very small. So it's macroscopic, the object. This is one example. And there are people going towards this type of experiments with levitated particles. So I would say that the number of people working in that regime is growing. The combination with gravity is sparse, if not to say absent. So I think that the biggest driver right now for going to levitated particles or more macroscopic quantum objects is really the sensing domain, because basically the more macroscopic your state is for certain external stimuli, you're very sensitive if you have if you use the coherence of your system. So for example, dark matter detection is now becoming a big field where they want to look at more and more macroscopic large masses to get a large cross section with the dark matter particle and quantum in order to get large sensitivity. Momentum squeeze it, for example, such that you get that is sensitive to kicks. Yeah.
Cool. And then my ignorance in the gravity is so I read in the public, this is not scientific, this is like public news kind of stuff, that there's some ideas that gravity will change as you change the size, the distance basically. So
yes.
Is this kind of what you would be able to detect here?
Yeah, definitely. It's very funny. So when we said that we now want to go to 10 micrometer as our technical challenge, I immediately got contacted by people from the high energy community who actually said, well, 10 micron, is really interesting because there are conjectures out there that at the 10 micron scale, there should be, if let's say some quantum theories of gravity are correct, and there the idea is essentially higher dimensions. Yeah, that's one of the reason why gravity is so small in the hierarchy problem is because there exists higher dimensions. This would only show up if you would look for gravitational phenomena at much smaller length scales. And there seem to be, I also didn't know that, there seem to be conjectures out there that the micron scale is exactly what everyone is hoping for. But yeah.
Okay, how long do you think it will be to cross these 10 orders of magnitude to get to 1?
Actually, I have an answer to that, because people are always asking me that, so I prepared a slide for it. So here's my answer. So this is this shows what happened over the last 20 years. So we started in 2004. Okay, so left upper corner. We started basically with the question, oh, can we have those solid state systems and control them in a quantum regime with quantum optics methods? And that took us around 10 years. So the first 10 years was like trying to get quantum control. This we eventually achieved. Then 10 years later, we already had these first ideas with entanglement, with gravity and quantum. And then we started this levitated stuff. And it took us another 10 years to go to the quantum control of levitated solids, about what I showed you today. And we already did the first gravity experiments. And so the next 10 years, this is our roadmap. So on the quantum side, we just now need to go on and delocalize small masses, delocalize cold small masses, and then delocalize cold large masses. So this is our 10-year time scale. And on the gravity side, we now measure Planck mass. In a couple of years, we have the 10 micron scale, and then we just need to do 10 to the minus 3 times Planck mass at micron scale. Right? And then we combine it. And then actually you are at 15 years, which is approximately the time scale you have in Europe before you reach retirement age. Right? So this is actually what sets the time scale. Mandatory retirement in the European system.
That's a good place to stop. Thank you very much, Markus, for the wonderful talk.